Electric fields. In this video we'll go into more detail about electric fields and also a few different scenarios. An electric field is defined as the force per unit positive test charge placed at that point in the field. So what that means is the force is calculated using Coulomb's law, and the charge there, Q, is the charge of the particle that's in the field. Now when we're talking about unit positive test charge, the unit just means 1, so we use a value of 1, and that allows us to simplify the equation. So in this scenario we're looking at what the electric field is at point A, and we're going to have a positive unit test charge of Q in that location. Okay, so first we find the force on that point. So we can use Coulomb's law for that one, which is this equation. Now in Coulomb's law equation, we've got two lowercase letter q's. In this one we've got an uppercase Q, and all that means is that that's maybe the bigger charge or the charge we're concerned of here. The force on the charge lowercase q at this point is denoted by that. But to find the electric field, we use that force, divide it by that charge, and we end up with this result. So what ends up happening is that lowercase q and that lowercase q cancel out, and it means the electric field at that point is not influenced by this lowercase q, and the electric field at that point is just due this main charge here. So this slide is kind of an extension of the last video where we were talking about multiple charges in a certain area and determining the resultant force. Here we're looking at the resultant electric field. Okay, so we've got two charges A and B, and we want to know what the resultant electric field is at point P. Now point P can be any point. In this particular case we're just using this one. Okay, so Coulomb's law states that the force is related to 2 points, so we can only look at 2 points at one time. So first let's look at point A and then point P. Now if we're looking at a positive test charge, which we always are in electric fields, if that's a positive test charge, the resultant force is in this direction here. Okay, and I've written A there because it's due to A. Now in the second case we're looking at B and P, and the resultant force is out in this direction. Okay, now because they're vectors, we have to add the vectors at point P to determine what's actually happening at point P in terms of the electric field. So looking at vector B and vector A, adding them together we can do A plus B or B plus A. In this case I've done B plus A head to tail, and the result is from start to finish, so from here to here, and it's this yellow line. So really what's happening over here, if we move that yellow line over, when we have two charges that are the same at point P, the electric field wants to go out in this direction. Alright, don't need you to take notes on this slide, but I'd like you to pause it and have a look at a situation which is similar to the one on the previous slide. However, this one goes through the calculations. Now we're going to have a look at a couple of example cases of electric fields. We've got two diagrams here of hollow conductors. Hollow meaning there's nothing in the middle, and conductor, it's a piece of metal that's in this case charged. So on the left hand side it's got a positive charge, meaning there's an absence of electrons, and on the right hand side it's got a negative charge, which means we've got an excess of electrons. Let's take a look at the right hand side. Because there's an excess of electrons, these electrons want to be as far apart as possible from each other, and being in a static case, meaning they're not moving around, they are as far apart from each other because of the repulsion forces. Now due to this, they exist on the very surface of the material, because that's as far away as they can get. If they were any further towards the center of the sphere, they'll be too close, so they exist exactly on the outside. Now because of this, if we take an electron on one side of the sphere, the forces due to that charge are balanced out by the electron exactly on the opposite side. What this means is there's no electric field inside the sphere. Now external to the sphere there is an electric field, and remember it goes at right angles to the surface, so every arrow here is at right angles to the sphere. Field strength is strong close to the sphere and weaker further away. Now the same with the hollow conductor. When you have a solid conductor, those excess charges want to be as far away from each other as possible, and they also, the majority of them, exist on the external part of the sphere. And again, any field that's radiating inward, so if we had a positive test charge, for example, at this point here, this charge and this charge will have a balanced force on it, and all the forces will cancel out, so that there's no electric field inside the sphere. Alright, so electric fields always leave and meet surfaces at right angles. Let's just take an example as if this wasn't the case, we would have something like this. So if it wasn't at right angles, it would be at an example angle out like this. And taking the components of this electric field, we might have this component here, which is perpendicular to the round object, and we have this component here. Now what this one suggests is that the electric force or the electric field is along the surface of the material, and it suggests that the electron, in this case, will be moving, but that's not the case. So in a static situation, meaning when the particles are not moving, the field lines are perpendicular to the surface. Conductors like metals contain electrons that are not bound to the individual atoms but are free to move around the material. Okay? These are called free electrons. When we have a solid uncharged conducting sphere introduced between two parallel plates, those electrons in that sphere will move towards the positive plate. They'll be attracted to it and they'll physically move within that material. So what happens is that the electrons move towards this upper surface as shown in the diagram, and the field is distorted as shown here. So the important things to consider in this diagram is that we've got a uniform field away from the sphere. So the lines here are equally spaced and traveling in the same direction. There's distortion at the ends, which is traditional in finite parallel plate situation. So you've got that curved field line at the end. Closer to the sphere, the field lines are slightly distorted, like seen here. The electrons move to the top of the sphere. The bottom of the sphere becomes positively charged because there's an absence of electrons there, and the field lines are denoted like that. Okay, we've discussed this before, but there's no electrical field inside a hollow conductor of any shape. So we've been talking about the spheres, but if you have any other shape, being a cone shape, even in that situation, there's no field inside the cone because the forces still balance out in a static equilibrium. The only way to create an electric field inside a hollow conductor is to place a charged conductor inside that. Okay, but then ultimately, right in the middle there, there's still no field. Okay, this diagram again is similar to the one we were looking at previously. Instead of a solid conductor, this one is a hollow conductor. Similar situation where the electrons move to the surface at the top. In both cases, there's no electric field inside this conductor. Alright, so what are the important factors that influence the magnitude and direction of an electric field in space? So I'd like you to think about what the equation of an electric field is when trying to explain this.